right? So that is horn gate, right? Basically smooth curves, that is the characteristic of it. And why we are keeping that is to avoid turbulence and mold erosion and oxidation also, right? Horn gate, and then you have parting type, right? Wherein most commonly used gate and is a compromise between top and bottom gate, right? So the two extremes, as we saw, top gate it's directly poured in from the top, bottom gate it's poured in from the bottom, right? So midway you have this parting type, right? It's a what do you call compromise between the two, or a hybrid type, you can say. It is most commonly used gate and is a compromise between top and bottom gates, right? The gate is provided at the parting line of the mode, as you can see. The gate is kept at the parting line. So it starts filling in exactly at the mid of the setup, right? Parting type gate. So those were the types. Now you see risering. As we have seen, a riser or feeder head is a vertical passage made in the coke to store the liquid metal and supply the same to the casting as it solidifies, right? That's what the purpose of the riser is, we have seen. Now, the different functions, right? What this riser does, apart from that two major ones, it stores sufficient liquid metal and supplies the same to the casting when it solidifies, thereby avoiding volumetric shrinkage of the casting, right? To avoid shrinkage, this riser will provide that molten metal. The riser must be kept open to the atmosphere and placed in such a location that it maintains a positive pressure liquid metal on all portions of the casting it is intended to feed, right? It is kept open, and there is even another one. This is not kept open all the time, as we will see in the different types. And it is placed in such a location that it maintains a positive pressure of liquid metal on all portions of the casting, right? So that riser is basically responsible for that positive pressure that is there, because that is the part where your molten metal can flow inside, right? Back inside. Once it has filled the mold cavity, right? It flows into the riser, right? So riser is the only point where it can come back, drop down to the mold cavity. That's what it means, right? So the cylindrical shape riser are generally recommended compared to spherical shape risers, which although are considered as the best. Okay, so most generally cylindrical risers are recommended or used. Now you see the types of risers. We have open riser, right? As the name suggests, the top surface of the riser will be open to the atmosphere. The open riser is usually placed on top of the casting, right? You have this mold cavity here, and this riser is kept above. So this riser is open to atmosphere, right? The atmospheric pressure acts on the molten metal directly, which is there. The molten metal which is there in the riser. Once it has filled the mold cavity, it will come to the runner. Riser, right? So the gravity and atmospheric pressure causes the liquid metal in the riser to flow into the solidifying casting, right? The gravity and the atmospheric pressure, two things. Gravitational force of the liquid metal and the pressure, atmospheric pressure, that will cause the molten metal in the riser to flow inside while the this molten metal is shrinking, right? And then blinder riser, completely enclosed in the mold and not exposed to the atmosphere. You can see here, this is your riser. This part is your riser. So you see that top atmospheric pressure is not there here. It is enclosed, right, inside. So that's what makes this a blinder riser. It's formally enclosed in the mold and not exposed to the atmosphere. The metal is cooled slower and stays longer, promoting directional solidification, right? It is cooling slowly, right? Completely enclosed, right? So the riser is also enclosed, so that would ensure a slower rate of cooling, and this will promote direction solidification. The liquid metal is fed to the solidifying casting under the force of gravity alone, right? As you can see here, this riser under the force of gravity, this will go inside this cavity as it is solidifying, right? Now, considerations for designing the riser. What are the factors? Freezing time is one factor, right? For producing a sound casting, the molded metal must be fed into the mold till it solidifies completely, right? So until the point that it solidifies completely, there should be flow of this molten metal, right? Freezing time. That is the criteria we're looking at. This can be achieved when molten metal riser should freeze at slower rate than the casting, isn't it? Because it is responsible for supplying that molten metal, and it is if it solidifies first, right? If it solidifies earlier than the casting, then the purpose is lost. So we have to ensure that this molten metal which is there in the riser should have a freezing time that is slower, the slower rate of freezing time as compared to the casting, right? Freezing time of molten metal should be more for risers than casting, as we have discussed. The quantitative risering analysis developed by Kane and others can be followed while designing risers, so that there is that empirical methodology developed by Kane, right, the researcher. So that is a quantitative analysis, right? Requires different quantities. And basically is about numerals, right? It's not a qualitative one, quantitative one based on dimensions and rules, etc. So that can be utilized to ensure that differential freezing time of the riser and the casting. Feeding range. When large castings are produced in complicated size, then more than one riser are employed to feed molten metal depending upon the effective freezing range of each riser, right? Bigger castings or complicated size castings, more than one risers are given, just as you have more than one gate, right? So you can have multiple entries to the mold cavity, multiple entry of molten metal to the mold cavity. You even have multiple risers. Okay, casting should be divided into different zones so that each zone can be fed by a separate riser, right? Instead of giving up one particular riser, you are having multiple risers. Those are responsible for supplying the molten metal to different parts of the casting. So riser should be attached to that heavy section which generally solidifies last in the casting, right? So that is another principle, that it should be attached to that heavy section which solidifies last. Heavy section in the sense it requires a lot of molten metal because there's more shrinkage there, heavy section. So that analyzer should maintain proper temperature gradients for continuous feeding throughout freezing or solidifying, right? The proper temperature gradient should be maintained, right? The difference in the temperatures for continuous feeding, right? Otherwise, it will solidify at once, like that. Other thing is feed volume capacity. The riser should have sufficient volume to feed the mold cavity till the solidification of the entire casting, right? So sufficient volume should be maintained of the riser, right? The cross section of that riser and the height of the riser should be so designed that you have sufficient volume to feed the mold cavity till the solidification of the entire casting. So you have this calculations done that after 2 minutes, the mold cavity is completely solidified, right? So you should ensure that before that 2 minutes, there should be sufficient volume in the riser to supply to account for the shrinkage, right? To compensate for the shrinkage. That is what is to be ensured. so as to compensate the volume shrinkage or contraction of the solidified metal. Metal is always kept in molten state at all times, risers during freezing of casting. It can be achieved by using exothermic compounds, an electric arc feeding arrangement. This does it reserves for smaller riser size and high casting yield, isn't it? Because if you want to ensure that the freezing of the molten metal which is there in the riser, it shouldn't freeze earlier in the casting. How do you ensure that? You keep some exothermic compounds, right, which keep the temperature high, or electric arc feeding arrangement also, right, that is responsible for increasing the temperature and therefore maintaining the temperature gradient between the molten metal in the riser and that of the the molten metal which is there in the mold cavity. So that this will result for a smaller risers, right? If you have that electric arc feeding arrangement or exothermic compounds, you can keep a small riser size. Otherwise, you would have to keep a larger riser size to have more volume. It is very important to note that volume feed capacity risers should be based upon freezing time and freezing demand, right? The time of freezing and the demand were at all required in the different portions of the casting. Is that clear so far? Okay. So you see, for an optimum riser design, the criteria to look at is the molten metal should be there in the right amount, or basically the riser, right? The volume of the riser, we can say, in the right amount, at the right place, at the right time, right? It should be able to supply the molten metal in the right amount, at the right place, at the right time, right? Because if it is not in the proper amount, then some part of the casting would receive the molten metal, right? And some would not. So amount is important. At the right place, right? Where it is required, if there is a section which is very thin, doesn't shrink much, and you're supplying more metal there, that's not required. So it should be so ensured that only thicker sections or complicated, wherever you have complicated features, there the shrinkage will be more, etc. like that. At the right time also. Once it is solidified, you're not supplying, doesn't make sense, right? So that's what this optimum riser design is. It should be able to supply the molten metal in the right amount, at the right place, at the right time. Key factors to look at. So that is your riser design, right? That we have seen. Now you see the last topic in our first unit is basically the guidelines for the casting. We'll quickly go through that. The first is avoid sharp corners, as we have already discussed, right? Instead of keeping sharp corners, you can provide fillets, right? So you have molten metal flowing smoothly, right? Use fillets to blend section changes smoothly, right? This V part, we have this fillets to blend those sections smoothly. And C1, avoid rapid changes in cross-section areas also, right? As I've explained in the diagram earlier, we're basically not having much bottlenecks, right? So that, and if unavoidable, design more to ensure easy metal flow and uniform rapid cooling, right? If that is not possible, to avoid those what do you call cross-sectional, change of cross-sectional areas, what can be done is the mode should be so designed that there is easy metal flow and uniform or rapid cooling by using chills or fluid cooled tubes, right? Directional solidification, extraction of heat should be ensured using chills, etc. As you can see here, these are different types of chills. They are kept at proper positions, right? For example, here, this part of the casting, is more likely to shrink when it is solidifying. So you are providing some chills here, right? And even here, those all spots. Okay, like here also for this boss, right? Extruded part, you're keeping a chip here also, like that. Here also, you see, to avoid that shrinkage, etc. Poor design, this is a good design. This one is a poor design. You have a lot of cross sections merging. So you have split them into different what do you call intersections. This one is a good design, right? You can even plot like this. So you don't have much drastic change in the cross sections. Avoid large flat areas, as you can see here. And warpage, you see, if you're not providing these reinforcement ribs, as you can see here, you see here three reinforcement ribs you have. If you don't provide them, then out of when it is solidifying and it shrinks, the dimensions would change of the geometry, right? It will warp or shift out of place. So even reinforcement ribs are to be provided where necessary, right? Where there is a chance that it will distort. And you see that this is why we avoid large and flat areas. If it is unavoidable, then you can keep these kind of ribs so that you can avoid this warpage and due to residual stresses, right? As it is well defined. Provide drafts and tapers. We have already discussed, right? Why to provide a draft and taper. Instead of having this straight portion, you can have it tapered. So there is ease of removal. This angle is called draft angle, right? The angle at which you are trying to take this inside, right? The feature inside, draft angle. So that there is easy removal of the pattern, right? So provide drafts and tapers, easy removal. It avoids damage to this mold cavity, this mold surface. Otherwise, there will be sand coming out of it, and therefore it will disturb the shape of the mold cavity. Account for shrinkage, geometry and shrinkage cavities you see here. For avoiding this shrinkage cavity, you are providing proper cross sections like that. Here also, shrinkage cavity, trying to have a proper channelized molten metal flow. Here also, you see, they have decreased this cross section, basically throat, so that there is not much area which is lying inside. If you have proper surfaces, more surface area is what we are ensuring here, right? To avoid the shrinkage cavities, right? Proper design of parting line. You see here, irregular parting line, right? Now you have designed it, redesigned it. Original design is this, improved design is this. So you have a straight parting line, right? Flattest parting line is the best, right? This one is the flattest one. This was not so. You have some part lying below that. So redesign based on this. So castability, you can say, can it be cast or not? So design for casting like that. All right, that ends the first unit. Okay, sorry for taking some more minutes. If there are any doubts, please ask. Meanwhile, I'll take the attendance. Okay. If there are no doubts, then we'll end the class. Okay. If you have any doubts, you can ask. Okay, then we'll end the meeting. Thank you.